given the vector function that we see here, and the elliptical paraboloid here, we easily see that the points of this vector function lie on the elliptical paraboloid, lie on the surface of this paraboloid. We just plug in x equals 5 minus t over 2, which is the I component, y equals t, which is the j component, and z equals what you see here, and we get this. And it's very clear that this term matches up with this term, and this term, if we square the 10t squared, we get 100t squared. Multiplied by 0.01, we just get t squared. So that this term matches up with this term, but these terms are negative, so we get 0. So the conclusion that we're on the paraboloid is valid. Okay, so here's a picture of the paraboloid. I constructed it. I can't reconstruct it. I used a rectangle here, a parabola here, the parabola corresponding to what happens if we let x equal 0, which is the case on this rectangle here above the y-axis. And of course, if x is 0, we get z equals 0.01 y squared. If we rearrange this a little bit, that's a parabola. When y is 10 or negative 10, we get z equals 1. So the parabola goes up to z equals 1 here and here. And we just sketch a parabola. And then we have a similar parabola. If we let y equals 0, then we're in the xz plane, and we get z equals 0.04 x squared. We can see that when x equals 5, z is going to equal 1. So we have a rectangle here sketched in the xz plane and a parabola that comes down to here, and there's a dotted line that goes on up to here. And then we just do a little shading. We also sketch the ellipse in the z equals 1 plane. If z equals 1, then this adds up to 1, and that's a parabola x squared over 25 plus y squared over 100, which gives us semi-major and semi-minor axes of 10 and 5, 10 parallel to the y-axis, so that we do get this point here that we got from the parabola, and this point here. And similar, this point and this point lie on the ellipse, the points that we got from the x parabola. So there's our ellipse, and then we shade a little bit. We sketch smaller and smaller sections of the visible parts of the ellipses that would go in the various z-planes. And there we have it. There's a picture. Now, the path r of t confined to the xy plane, if we let the z component equal the k component equal 0, as the path from here to here. These are linear functions. X is a linear function of t, y is a linear function of t. If you understand what we reviewed about parameterizations and so forth, we see that we get we can visualize this as constant motion from this point to this point. The points that lie above this segment lie on the paraboloid. This point lies above here, this point lies above here, and we have some sort of curve along the paraboloid that we could analyze. Well, to start to analyze it, let's do we imagine again that t is time and that we're moving along this curve. Our velocity function is the derivative of our position function, and that derivative is straightforward. We take that derivative. Our acceleration function is the second derivative of our position function, or the derivative of our velocity function, and that gives us a constant function, 0.04k. And then our unit tangent vector is just our velocity vector divided by its magnitude, and if I have that expression correct, it's here. So now we have unit tangent vector velocity vector, acceleration vector, and we're going to look at the projection of the acceleration vector on the unit tangent vector. Now we're going to get bogged up in a big mess. Or at least we did in class. I'm not going to get bogged down in that mess. But you see the basic picture and what we can say about that basic picture. And then we want to go on and talk about normal components, binormals, and curvatures. Again, in class we got bogged down on the details, so I kind of cut through the details. It turns out the calculations were too long to do on the board. I couldn't do them fast enough in my head to, and I didn't anticipate how long the calculations would be. I know they'd be long, but so that was a bad plan. But there's the picture of what we're doing.